Hello all. Today in this lecture we will be discussing about Rutherford backscattering spectrometry or RBS. RBS is a powerful analytical technique used for depth profiling as well as determination of stoichiometry of thin films and surfaces. It's really used to study about the composition and structure of the material at the atomic level. So basically RBS consists of three stages. The first one is the incident beam strikes on the surface. That is, a beam of high energy charged particles falls on the surface, reacting with or interacting with the required surface. And the second stage is the back scattering of the incoming projectiles. That is, the charged particles interact with the atoms in the sample or on the surface and which are scattered back at various angles. Among these all scattered particles, the back scattered particles will be having maximum information about the surface layers. And the third stage is the energy analysis. The energy of the back scattered particles are analyzed to determine the composition as well as the depth profile of the sample. So, the primary stage involves the Coulombic scattering. That means the interaction between incident charged particles and the atoms in the sample will be of Coulomb scattering type, where the particles are deflected by the electric fields of the atomic nucleus. And after that, as the Coulombic scattering occurs, the energy will be lost by the incoming projectile in a statistical manner. As charged particles travel through the sample, they lose energy through inelastic collisions with electrons, leading to a characteristic energy spectra. And that energy loss and study of that energy loss leads to the depth information. That is, the energy loss of the particles provide information about the depth at which the scattering occurred, allowing the stoichiometry determination and depth profiling of the sample. So, considering the mathematical or theoretical background, Rutherford backscattering or RBS works on the principle of elastic scattering process, where the total energy is conserved. As there is no internal excitation of either of the two partners, that is, the incoming projectile as well as the parent nuclei are not excited, the Q value of this process will be 0 and the reaction can be written as A plus X equal to Y plus B. In this case, Y will be as same as X itself and B will be A itself. But the energy of the particles may be changed after the collision. From the conservation of energy and momentum, we can have these three equations. The first one is for energy conservation and the other two indicates the momentum conservation in horizontal as well as vertical directions. By proper combining and solving these three equations, we get the energy for the outgoing projectile after deflection as EA prime being the energy of the outgoing projectile or the projectile after deflection, which is equivalent to EA by 1 plus R square 2 cos theta square plus R square minus 1 plus 2 cos theta root of cos square theta plus R square minus 1. In this case, R is the ratio of the masses of two nuclei, mx by ma, mass of the parent nuclei divided by mass of the incoming projectile. And the quantity within the square brackets, that is EA by 1 plus R square, is usually referred as the kinematic factor K, which is the ratio of projectile energy after collision to the projectile energy before collision. Or rather, it is a measure of the energy possessed by the outgoing projectile after the collision. And while considering the different various angles for scattering or collision after deflection, we can see for theta equal to 0 degree, the incoming and outgoing projectiles have same energy, which is obvious because if theta is 0, which means that it hasn't been deflected, so there won't be any interaction with the sample and there will be no loss of energy for the incoming projectile. But at 90-degree deflection, the energy of the outgoing projectile, that is EA prime, will be equal to EA times R square minus 1 by R square plus 1. And for backscattering, that is for at 180-degree backscattering, that energy would be EA prime equal to EA into R minus 1 by R plus 1, the whole square. And as you can see from these three results, the energy lost by the incoming projectile will be maximum when the angle is 180 degree. That is, as scattering angle increases, the scattered energy decreases. So the maximum information will be carried away by the projectiles which are scattered in backward angles, that is angles almost equal to 180 degree or above, say 150 degree above scattering angle, and hence the name is given as Rutherford backscattering. So backscattered particles contain maximum information because they interact with the sample with high probabilities. So we will be analyzing the energy spectra of the backscattered particle, which will yield the information about the stoichiometry and surface properties of the sample surface. Here, a plot is given for various angles of scattering. The relation is between the energy of the scattered particle with the ratio of masses. So there are so many plots, each of them representing different angles of scattering. The lowest graph represents the angle backscattering angle, that is 180 degree, and the topmost graph represents the results for 10 degrees. So as you can see from this plot, the resolution is maxima at lower R values, around 5 or 4 or below 5 this range. This resolution, that is the distinction between different graphs, are maximum. And as well as we can have another plot between scattering angle versus energy of scattered particles for different R values. And in this case you can see as scattering angle increases, the resolution is better. So we can conclude from these two plots that the mass resolution, that is separation between neighboring mass peaks or neighboring peaks in the R-base spectra, will be better at larger angles of scattering, and the resolution is better at lower R values. Right. So these are the experimental results for determining the or calibrating our system. And let us consider the Rutherford scattering process is actually it happens due to Coulombic scattering or Coulombic interaction between the particles. So the path of the projectile will be as shown in the figure, that is P A P prime. Here we have P A P prime. This is the path. This is my path of incoming and projectile, and our parent nuclei is located at the origin. Right. So the conservation of angular momentum implies that the scattering process is confined to a plane containing the initial velocity of the particle. That is, as it is a central force problem, and also considering the conservation of angular momentum, this projectile moves through, or this path P prime will be in a plane which contains the direction of initial velocity. And as it is a central force problem, the aerial velocity of this particle will be a constant. So considering these two, I can write these two equations. EA is equal to EA prime plus ZZE square by R, and that second term actually represents the Coulombic interaction term, and the other one MA VA into B, that is angular momentum, which is equal to MA into R square d delta by dt, where that delta is actually the polar angle created by the incoming projectile. This one is the polar angle, delta. And expanding the first equation using the kinetic energy equations, half ma Va square is equal to half ma Va prime square zz square by r. And solving for the velocity the velocity of the particle is composed of two parts. One is aerial velocity and the other one is radial velocity, that is dr by dt as well as r d delta by dt. Hence, the total velocity Vx can be written as like this. And from above considerations and assuming u equal to 1 by r, we can solve for u as, or we can form a second order differential equation du by d delta square whole square is equal to 1 by v square minus 2u by l plus a aerial velocity square, where the value L, which is in the second term in the denominator, L can be written as MAVA square B square by ZZ E square. And solving for this differential equation, I can calculate the value of R, which is the distance. R is equal to 1 by epsilon cos delta minus 1. R is equal to L by epsilon cos delta minus 1, where this epsilon is also represented as root of L square by B square plus 1. So, considering this equation, so this one is a familiar equation for us, and that is the equation for a hyperbola. So, this represents a hyperbola with target nucleus as one of its foci. That is, the path of the projectile will be a hyperbola. And the closest approach, the distance of closest approach of the projectile can be obtained as like this, Z minimum, right? The minimum distance between projectile as well as the target nuclei as the Coulombic interaction occurs, and say this will be the least value for head-on collisions, and therefore that theta will be equal to 180, and as a result we will be getting the least distance of closest approach, that is d, which is equal to ZZ square by EA. And the impact parameter can also be determined from this, and that impact parameter B, which is equal to ZZ square by 2 EA cot theta by 2. Right. So, while considering the cross section of this Rutherford scattering, we can have two approaches. The first one is the classical approach, which is the simplest one, and we say that the projectiles with impact parameter between B as well as B plus delta B, they will be scattered through angles lying between theta and theta plus delta theta. That is B, impact parameter B will scatter through angle theta as well as B plus delta B will scatter through angle theta plus delta theta. So, this process is having an azimuthal symmetry, as it is to be symmetrical to the axis, and the probability of scattering through angles between theta and theta plus delta theta, or within the solid angle d omega or d omega at the nuclei, that will be given by the area of the annular ring shown here. This one, the area of this annular ring with radius b or average radius b and thickness db, right. So, this is simply having an average radii b, and the thickness of this thing will be delta b or db. So, that area can be calculated as the cross section, that will be minus 2 pi b db. This minus sign indicates that theta plus delta theta is less than that of theta, right. As impact parameter increases, the scattering angle decreases. And using the equation of impact parameter, as b is the impact parameter and db can be calculated from that. So, using that cross section can be expressed as d sigma by d omega will be equal to 1 by 16 ZZ square by 2 ES the whole square cosec theta by 2 whole raised to 4. So, which is the very famous Rutherford scattering formula. So, this is the classical approach where we are considering all the particles between impact parameters B as well as B plus delta B. So all the particles are considered, so that we should consider the annular ring and the areas being determined. In quantum mechanical concepts, the incoming projectile can be considered as a plane electron or plane wave which is traveling along the positive z direction, so that I can consider the wave function as psi incidence, or the wave function for the incident wave should be equal to e raised to I kz. Right? This is an equation for, or this is an expression for a wave traveling or plane wave traveling along the positive z direction. Right? So as the angular momentum is conserved in this interaction, it is usual to expand the plane wave as sum over partial waves designated by quantum number L equal to 0, 1, 2, 3, etc. And each partial wave can be written as a superposition of an ingoing and outgoing spherical waves. Right? This plane wave can be expressed as the sum of different partial waves, and each of them are represented by their corresponding quantum number L value, and L equal to 0, 1, 2, 3, etc. And each of these partial waves can again be split into sum of two spherical waves. Right? Sum of two spherical waves, one is ingoing, that is converging to that point, and other one is emerging from that point. So superposition of these two gives out a plane wave. And among these considerations, only the spherical wave that is emerging out or the outgoing waves are affected by the scattering potential. Right? The scattering potential arises as the projectile approaches the surface or approaches the parent nuclei. So the nucleus produces the scattering potential. So that I can represent the scattered wave function as a spherical wave which is emerging out from a point, that is psi scattered is equal to f of theta e raised to I k r by r, which is a equation for the spherical wave. Here the f of theta is called the scattering amplitude, and in this case f of theta will be this much, that is zz square by 2 MAVA times cosec theta by 2 the whole square, and the square of this f of theta, that is scattering amplitude, gives out the scattering cross section. And surprisingly, both classical as well as quantum mechanical approaches yield the same result. But this Rutherford formula breaks down for light nuclei and for high energies. So under such conditions, that is at high energies as well as for lighter nucleus conditions, we have to add Born approximation. Right? We will employ Born approximation in such cases, which yields a result like this. So this is the equation for the scattering cross section under high energetic condition as well as for lighter nuclei. And this plot here actually represents the relation between the scattering cross section as well as the scattering angle. As you can see here, as the scattering angle increases, this cross section gradually decreases. So for RBS, we have to choose wisely the scattering angle and the cross section value. Thank you.